So we're leaving the moon and welcoming Eberhard Gruen.
Thank you. Okay, this is work in progress. My collaborators are Rachel Surya and Max Sommer from the University in Stuttgart. We so far looked at a specific example for Comet Churyumov-Gerasimenko, with over the next months we hope to get much more information on the release of meteoroids from a comet, namely from this comet through the Rosetta mission. Therefore, that's what we concentrated on so far. Why do we want to know this? Now, the major sources of the meteoritic complex are asteroids and comets. And from the dust and meteoroids released from these comets, several processes act on them which distribute them in space and time and mass-wise. And from the observations, we know that for small particles, smaller than about 100 micron in size, or 10 to the minus 6 grams, we know that the distribution is smooth, both in space, in mass, and in time. However, for the bigger particles, bigger than about 100 micron, the distributions are rather granular. And that is important because that tells us how the mass from these objects, which are point sources, then spread through the solar system and is changing with time. And the big particles, of course, are the main source for the meteoroid complex. But for the exploration aspect, there is another important aspect. The big particles, bigger than about a 10th millimeter, up to a centimeter and more, they pose a hazard. We better know where they are, where to expect those. Here are two aspects of the meteor streams. One is when the Earth accidentally passes through one of the meteor streams, like here in the upper panel, through the debris from Comet Tempel-Tuttle, then you see a meteor storm, a high frequency of meteors with high speed impacting the Earth and generating meteor phenomenon. And even the space agency are concerned about, at these times, about their satellites. However, that's only visible when the Earth passes through it. Now, there's another method to look at these in space, and that's through infrared observations. And one of the earliest infrared space telescope, the IRIS mission, looked in the mid-infrared wavelengths, 10 to 100 micron, and it saw trails along the orbit of comets, in this case of Comet Encke. And these trails, in recent observation by Bill Reach with the CERTEF instrument, found that 80% of the Jupiter family comet or short-period comets he looked at have trails like this. So there are a lot of meteor streams in space crisscrossing space, and we better know how they are distributed and what their lifetimes are. So we look at various aspects of the lifetimes. First, the spreading of the fragments or the emitted particles from the comet along the orbit. Then we look at what the planetary scattering does, specifically Jupiter, because that's the 500 kilogram gorilla in the solar system steering up the meteoroid complex. And then we look at what collisions with mutual collisions with the meteoroid environment is doing to it. And also a smaller effect on smaller particles upon Robertson, which moves then small particles towards the sun where they evaporate or be injected as beta meteoroids. Now the spreading along the orbit here, I show an example from particles released from Churyumov-Gerasimenko, the smallest particles we looked at, 10 to the minus 6 gram particle, a typical emission speed of 30 meters a second, which comes in addition to the comet speed of in the inner solar system of 35 kilometers per second. But this small addition, 30 meters, causes a different semi-major axis, different energies of the particles, and therefore different semi-major axes mean different periods, and therefore they spread along the orbit. And you see here various aspects of it. The height of the meteor stream above the orbital plane, and the scale you probably cannot read it, that's 1 million kilometers, 10 million, 100 million kilometers. So the height of the stream is oscillating from perihelion to aphelion in the range of a million kilometers or a few million kilometers. The radial width is somewhat larger, up to about 10 million kilometers, but it's repeating. It's not spreading in these dimensions, while it's spreading along the orbit, again oscillating. Now the volume of such a stream is increasing with time, oscillating again, until the full orbit is filled, and then only oscillation happens. And that occurs under these conditions within a few hundred years. Then the dust has filled the ring around the orbit of the parent comet. Okay, the second aspect, we want to look at Jupiter scattering, and we did calculation, namely we started with about 10,000 particles spread along the orbit of Churyumov-Gerasimenko, and we looked at the conditions in 1959 when Jupiter passed very close to the comet and put it on a different orbit, namely the one which it is on now. The comet moved within the orbit of Callisto, one of the outer Galilean satellite. Now, and we want to look how these particles spread along the orbit are changing. And you see within 2 years after this event, Jupiter passing through this region with the node of the orbit, then some particles are strongly scattered from the original part, and I mark them in red. About an orbit later, a gap has developed and particles are spread around already significantly. And about 100 years later, the ring has closed again, the gap has closed again and widened somewhat, but the particles, the red particles, are scattered into interplanetary space. We look a little bit closer. Here are the orbital parameters, semi-major axis. The initial one were on this line, but then Jupiter caused quite some changes in semi-major axis, as in eccentricity and inclination. And where any of those parameters is beyond the limit, which you cannot see here, then I mark them red. Here I show in the eccentricity semi-major axis plane how these particles are spread. They started all at this position, and then the red particles are spread at quite some different orbital elements, while the Tisserand parameter stays the same. Important is here to note that these are the limits of orbits which cross Jupiter's plane, and this is a Tisserand parameter is 2.75 for these particles. That stays the same, but that occupies a significant part. So with multiple scattering, particles will stay within this region. This dotted line is the inner edge of the Saturn scattering zone. But at this scattering, not yet Saturn was reached, but due to multiple scatterings, planetary scatterings, the particles could pass from one planet to the next one, or get lost into the sun or ejected. So the third aspect, I want to look at the collisional shattering. The parameter which describes collisional shattering is this gamma factor, which is a ratio of any given target mass, our meteoroid, over the mass of the smallest particle which can catastrophically disrupt it. Catastrophically disruption means that the all the fragments from both target and particle are smaller than, let's say, half of the original target mass that we call collision. And from lab experiment, you get a function for these gamma values, which is shown here, which has a strong speed dependence and a mass dependence. At 20 kilometers, for example, the smallest particle, the mass ratio is 10 to 4 between the target mass and the small fragmenting projectile, up to several 10 to 5 times the target, the projectile mass. So this is a significant factor. In order to estimate now the collisional lifetime, we have to fold in a model, and we taken the meteoroid model from which was developed by Valery Dikarev in 2005, and which is the basis for the ESA interplanetary meteoroid model. And now, for various positions along the orbit, we calculate for various directions, the RAM direction, anti-RAM direction, port, starboard, north and south directions, the flux of colliding meteoroids, which are smaller than the meteoroid we are looking at. And we calculate this and came up here, for example, the flux for the given target mass, which are the projectile mass which contribute most, and at what is the impact rate for these catastrophic collisions. And if we add this all up, then we come to this solid line. This is the lifetime of particles of this mass here, 1 gram, as a function of the size in years. That's so the short, about 1 gram particles live about 10 to 4 years with respect to collisions, after which they then fragment and contribute to smaller masses. For comparison, I show the Ponting-Robertson lifetime, the red line here, and this is more or less negligible in the mass range which we are considering. For comparison, I show it also the lifetimes for 1 AU circular orbit, which we published already some time ago, and it's rather similar. So in conclusion, the timescales and lifetime scales for Jupiter family comet type orbits is for the spreading 10 to 100 to 1,000 years. Jupiter's scattering is of the same order. This here, of course, depends on the emission speed, which we have not a good handle yet on. Hopefully, through Rosetta, we'll get better handle on the emission speed for at least this one specific sample. The Jupiter's scattering does not change the particle in size, but it moves them around in the planetary system and out of the stream. They are no longer concentrated then in the stream, but collisional shattering of all the particles on this type of orbits is of the order of 10 to 4 to 10 to 5 years. And the Ponting-Robertson effect is negligible. So this concludes my presentation. Thank you.
Have time for a few questions? Yes.
So I've got a question about the model that you're using. I've got a question about the model that you're using for the orbital dynamics. So you start out with a population of basically non-interacting particles and then set them off, or how do the original particle, when you're doing the spreading, are the particles?
The spreading, you mean the initial spreading due to the initial conditions?
Yes, yes.
Oh, now, we, at the time during the perihelion passage, we release particles in various directions at various speeds according to the size of the best models available and let them expand in time.
Okay.
Yeah. So, yeah. No big secret here. So.
More questions?